Hello everyone. What we're going to look at today is the relationship of the windings of this servo motor and the Hall effect feedback. Now, both the windings of the servo motor and the Hall effect feedback have a relationship between each other. And I'm always curious about these relationships. I don't know why that is. It ain't nothing special. But I'm always curious about things that are joined together mechanically. And I want to see in my mind these relationships. What we do here is we want to rotate the servo motor, and when you have the magnets of the rotor cutting across the windings of the stator, it will generate a voltage. And this is the reason we want to mechanically couple that motor to a DC motor so that we can rotate that rotor within the windings of that stator, and that will generate an AC voltage. And we're going to look at that AC voltage at the same time as we look at the Hall effect feedback. Now, this variac down here will put out a variable AC voltage. We rectify it with the bridge rectifier and filter it with these bus capacitors, and then run it into this DC motor. And that DC motor, mechanically coupled to the servo motor, will rotate this servo motor right here. So when we increase the AC voltage here with that knob, we increase the DC voltage here and increase the speed of the DC motor, which increases the speed of the servo motor. Let's look at the next page. This is going to get deep here, so hold on tight. Now, Siemens calls their Hall effects RLG-R, RLG-S, and RLG-T. What I've got to do, this is the motor over here, back over this way. What I've got to do is I've got to put 10K pull-ups on those three outputs. That Siemens servo motor requires 15 volts DC and ground on pins 4 and 5. Hall effect R, Hall effect S, and Hall effect T are on pins 3, 1, and 2. I've got an external power supply over here that makes the 15 volts and ground to power up those Hall effects. And here we have 3 10K pull-up resistors. They're 1/4 watt to pull these 3 Hall effect outputs up to 15 volts. Now you be careful. Your Hall effects might require 5, they might require 10, they might require 15. Your Hall effects may require a different voltage from an external power supply, so you need to check your the data sheet for your servo motor so that you put the correct VCC and ground into your Hall effect input on that motor. Siemens wants 15 volts. Yours might need 5. You need to double check your data sheet on your motor. Now, to connect the U, V, and W to this system, we're looking at it with a scope. You'll see it in just a little bit. You'll see it in a scope in just a little bit, but we want to tie V. This is the motor connection right down here. We want to connect V to ground right here. And we want to take channel 2 of the scope to U. And then we're going to, in the first instance, we're going to look at channel Hall effect R on channel 1 of the oscilloscope probe. So, Hall effect R, and yours might be labeled different. It's okay. Yours might be HE1, HE2, HE3, Hall effect 1, Hall effect 2, Hall effect 3. That's okay. This will work for your system. Here we're going to take Hall effect R and connect it to channel 1 oscilloscope probe. We're going to take motor winding phase U, and we're going to connect it to channel 2 oscilloscope probe. And then we're going to take motor winding V and connect it back up to ground here. Okay. Now the probe's grounds, you'll have a channel 1 probe ground and a channel 2 probe ground. Those probe grounds get connected back to ground here of the external power supply and the ground for the Hall effects inside the motor. It's one thing you got to be very careful about here. You want to isolate your CRT oscilloscope from earth ground, and you do that with a 1-to-1 transformer on the line plug or an isolation adapter on the line plug. Make sure that you don't have that oscilloscope, that CRT oscilloscope connected back to earth. And when you do this, when you isolate that scope from earth ground, don't touch no metal. Do not touch no metal on that oscilloscope, because that high voltage that we're seeing right here will find its way back to earth through you. When you isolate your scope off of earth ground, don't touch no metal. Now this, here we're looking at Hall effect R in relation to U and V. V going back up to ground, U going to channel 2 of the oscilloscope, Hall effect R going to channel 1 of the oscilloscope. Next thing we're going to look at, let's get this out of the way. We're going to look at the motor winding U on channel 2 of the oscilloscope, V on ground. But here we're going to look at Hall effect R on channel 1 oscilloscope probe. Now let's just go through real quickly the relationship of Hall effect T to channel 1, and here's U, channel 2, and V on ground. Okay, now look at this, we've changed a little bit. Hall effect R to channel 1, Hall effect U to channel 2, and W going to ground. And here we go with U on channel 2 and W to ground of the system that we've got set up. We're going to look at channel 1 to Hall effect S. Now we're going to look at U to channel 2, W to ground, and there's Hall effect T. We're going to look at that next. And here we've changed up on, we've gone from U, now we're going to look at V on channel 2, W on ground of the system, Hall effect R on channel 1. Oh, we dropped one. Get back up here, don't be squirrely. Okay, now we want to look at Hall effect S on channel 1 scope probe, V on channel 2 scope probe, and W on ground. W goes to ground of the Hall effects and ground of the external power supply here. Now lastly, what we're going to look at is Hall effect T on channel 1 oscilloscope probe, the channel 2 oscilloscope probe is going to be looking at V with W grounded to the system we have here. Ground on the feedback connector pin 5 and ground of the external power supply. Don't worry none, folks. I'll put these diagrams up at the end of the video and you'll be able to watch them, or you'll be able to take screenshots of these diagrams here at the end of the video. Now let's get to looking at the waveforms. I'm going to connect some wires to U and V of the motor windings so we can look at the relationship of the motor windings to the Hall effects. Come back here, don't get squirrely. Okay, there's a wire on U. There's a wire on V. We're going to hook channel 2 scope to U. We're going to hook V to the power supply ground. That's powering up the Hall effects. Start the DC motor. Bring the DC motor up to speed. The DC motor is rotating the Siemens servo motor. Okay. The top waveform at 10 volts per division is Hall effect R. The bottom waveform at 20 volts per division is U with W grounded to the 15 volt power supply. The 15 volt power supply is powering up the Hall effects. At the end of the video, I'll have diagrams of the setup that you can take screenshots of. Now notice where the peak falls in relation to the Hall effect. Now I'm going to move channel 1 scope probe to Hall effect S. Let me slow the motor down, stop it. Okay, now channel 1 is looking at Hall effect S. Let me start the motor. Okay, this is Hall effect S. This waveform down here is U with V grounded to the 15 volt power supply. And look at that. The peak of this UV waveform is perfectly timed with Hall effect S. Let's move that up. Look at that. I'm using the up button on the scope to move channel 2 up into channel 1. Look at that. That is perfect. Okay, let me move that back down out of the way. Okay, I'll slow that motor down. Now we're going to look at Hall effect T in relation to U and V. Speed the motor up. Okay. The top line is now Hall effect T in relationship to U and V. And right here is where it comes out at. That is very interesting. This waveform right here is the generated voltage derived from rotating the armature of that Siemens servo motor. And the reason we have to use an external drive source, that DC motor coupled to the shaft of the Siemens servo drive, is because we wouldn't be able to hook our scope to U and V if we were driving U and V and W with a servo drive, you wouldn't be able to look at this generated voltage if we didn't rotate that motor with that DC motor. Okay, let's slow the motor down. Let's slow that DC motor down and stop it. And turn the power supply off. And we're going to move our U and V connections on the motor windings to U and W. And we'll look at the relationship between U and W with respect to the three Hall effects. Okay? Alright, let's turn on that 15-volt power supply. We'll start the DC motor. Now that's interesting. This is Hall effect R. This is V with W connected to power supply ground. Now look here, we're in perfect alignment with Hall effect R at its lowest point. Let me slow the motor down, stop it, and we'll move channel 1 probe to look at Hall effect S. Speed the motor up. And the peak of V and W fall in that just inside the trailing edge of Hall effect S. I'd almost be forced to say that this peak here of U and W fall within 120 degrees of Hall effect S there on the tailing edge. It looks like it. Slow that motor down, and I'll move channel 1 probe to Hall effect T. Speed the motor up. Now we're looking at Hall effect T on the top waveform, and U and W on the lower waveform. And here we fall within the beginning of Hall effect T. Okay. Let's slow the motor down and stop it. The next waveform we're going to look at is V and W in relation to the Hall effects. So let me move those motor wires over and we'll test for that. Okay, let's speed the DC motor up. Okay, the top waveform is pin 3, Hall effect R. Now the bottom waveform is V on channel 2 probe with W grounded to the 15 volt DC power supply that's powering up the Hall effects. Okay, let's slow that motor down. Stop it. And I'm going to move channel 1 scope probe to Hall effect S on pin 1. Okay, we'll start the motor. Okay, now the top line is Hall effect S. The bottom line again is motor winding V and W. Slow the motor down. And we'll stop it. Now let's look at Hall effect T in relation to V and W. Start the motor. Look at that. Hall effect T is in alignment with the motor windings V and W. That's amazing. Alright, folks. That's how you can look at the relationship of the Hall effects with the motor windings. That's amazing. I like that. All right. Okay, let me slow that motor down. Stop that motor and I'll turn off that 15 volt DC power supply.